Have you ever walked past a tree that looked perfectly healthy, only to hear later that a large branch failed or the entire tree fell? Tree failures usually do not happen randomly. Trees do not simply decide to fail. In many cases, failure is the result of multiple factors coming together over time: structural defects, biological processes, environmental conditions, and mechanical forces. Today, we're going to explore the science behind tree failure. We will look at some of the most common structural defects, why they develop, how they affect tree strength, and what arborists look for when evaluating a tree. By the end of this lesson, you'll have a better understanding of how trees support enormous forces, how they adapt to their environment, and why some trees eventually fail. Before we talk about defects, it is important to understand something fundamental. A tree is not just a tall piece of wood. A tree is a living structure that is constantly growing, adapting, and responding to its environment. Every day, gravity places a constant downward force on the trunk, branches, and leaves. Wind creates additional forces by pushing, pulling, and twisting the canopy. As branches become longer and heavier, the amount of stress placed on their attachments increases. Rain can temporarily add significant weight to foliage, and saturated soils can reduce the ability of roots to effectively anchor a tree. Unlike a steel beam or concrete column, a tree is capable of responding to these forces through biological growth. When trees experience mechanical stress, they can adjust their growth patterns and produce additional wood in areas that experience increased loading. This process helps trees adapt to changing conditions. However, trees have limits. When the forces acting on a tree exceed the strength of the wood, branches, trunk, or root system, failure can occur. Tree failure rarely has one single cause. In most cases, several factors interact together. A branch may become longer and heavier over many years, increasing the leverage acting on its attachment point. Internal decay may gradually reduce the strength of the wood. Repeated wind exposure creates cyclic loading, placing stress on the tree structure through thousands of weather events. Eventually, a major storm, heavy rainfall, or another environmental event may become the trigger that causes failure. This is why arborists do not simply ask, "Does this tree have a defect?" They ask a more important question. How does this defect affect the tree's ability to support the forces acting upon it? This is the foundation of professional tree risk assessment. A defect by itself does not automatically mean a tree is dangerous. Arborists evaluate how the defect interacts with the tree's overall structure, environment, and the potential targets around it. One of the biggest misconceptions about trees is that only dead or dying trees fail. In reality, many tree failures occur in trees that are alive and actively growing. A tree can have healthy foliage, good color, and vigorous growth while still containing structural weaknesses that developed years or even decades earlier. Defects, such as poor branch attachments, included bark, internal decay, cracks, or root problems may not be visible from a distance. On the other hand, some dead trees can remain standing for many years depending on factors such as species, size, wood properties, environmental conditions, and location. Tree health and structural stability are related, but they are not the same thing. A healthy tree can still have structural problems, and a declining tree may still be structurally stable. That is why arborists evaluate both biological condition and structural integrity during an inspection. One of the most common structural defects arborists encounter is called included bark. Normally, when two stems join together, wood from each stem grows together to create a strong structural connection. However, sometimes two stems grow so closely together that bark becomes trapped between them instead of being pushed outward. Because bark is not structural wood, the attachment does not develop the same strength as a normal wood-to-wood connection. As the stems continue increasing in size, mechanical stresses increase at the attachment point. Over time, cracks may develop along the included bark union, and under sufficient loading, the stems may separate. Included bark is especially common in codominant stems, where two or more stems develop with similar size and compete to become the main leader. For arborists, identifying included bark early is valuable because young trees can often be improved through structural pruning before the defect becomes more significant. By reducing competition between stems early in a tree's life, arborists can help encourage stronger structure as the tree matures. A codominant stem occurs when two or more stems develop with nearly equal size and importance instead of one clearly dominant central leader. Codominant stems are not automatically hazardous. Many trees naturally develop multiple leaders and can remain structurally stable throughout their lives. However, some codominant stems deserve closer evaluation, especially when they develop narrow angles, included bark, poor attachment structure, or significant weight imbalance. When two major stems grow together, the attachment point can experience increased mechanical loading because both stems contribute weight and movement during wind events. As the tree matures, these unions may become important inspection points because a failure at a major stem attachment can involve a large portion of the canopy. This is why arborists evaluate not just whether a tree has multiple stems, but how those stems are connected, how they have developed over time, and how they respond to the forces acting upon them. Trees can develop cracks for many different reasons. Some cracks are caused by mechanical stress from wind loading, while others may develop because of previous branch failures, lightning strikes, rapid growth, temperature changes, or internal decay. Not all cracks have the same level of significance. Some cracks may only affect the outer bark, while others may extend deeper into the structural wood of the tree. The importance of a crack depends on several factors, including its location, its depth, its orientation, whether it is associated with decay, and whether it continues to change over time. Cavities are another feature that often concerns homeowners. A cavity does not automatically mean a tree is dangerous. Many trees can survive with hollow areas because trees do not need every portion of their interior wood to remain intact. The important question is how much sound, functional wood remains and where the loss of wood is located within the tree. This is why arborists do not make conclusions based on one feature alone. A cavity, crack, or defect must always be evaluated in relation to the entire tree and the forces it experiences. One of the most challenging parts of tree inspection is evaluating internal decay. Decay is a natural ecological process caused by fungi breaking down wood. Different fungi affect wood in different ways. Some fungi primarily break down cellulose and hemicellulose, while others break down lignin as well. These different decay processes can have different effects on wood strength. The important thing to understand is that decay can begin inside a tree long before obvious external symptoms appear. A tree does not heal damaged wood the way an animal heals an injury. Instead, trees respond to damage through a process called compartmentalization. Through compartmentalization, Trees create chemical and physical barriers that help limit the spread of decay organisms into healthy wood. This process is often described through coded compartmentalization of decay in trees. However, compartmentalization does not eliminate decay, it helps slow and contain it. Different species have different abilities to compartmentalize decay, which is one reason species identification is important during tree assessment. The presence of decay alone does not automatically mean failure is likely. Arborists must evaluate where the decay is located, how extensive it is, and how it affects the remaining sound wood. Many people focus on what they can see above ground, but some of the most important structural problems occur below the soil surface. Roots provide several critical functions. They anchor the tree, absorb water and nutrients, and help support the structure against environmental forces. Problems such as root decay, severed roots from construction, girdling roots, poor soil conditions, compacted soils, or restricted rooting volume can reduce a tree's stability. During major wind events, some trees do not break at the trunk or branches. Instead, the entire root plate can rotate because the anchoring system can no longer resist the forces created by the canopy. This type of failure is often called root plate failure or wind throw. This is why arborists pay close attention to the root flare, surrounding soil conditions, changes in grade, excavation or construction activity, signs of root damage, and the overall growing environment. A tree's stability begins underground. One of the most important concepts in tree biomechanics is leverage. Long branches behave much like long levers. As a branch extends farther from the trunk, its weight creates greater bending forces at the attachment point. The farther the weight is from the point of attachment, the greater the mechanical stress placed on that union. Additional factors, such as leaves, rain, snow, or strong winds, can increase those forces even further. This is one reason arborists may recommend reduction pruning on selected limbs. The goal of reduction pruning is not simply to make a tree smaller. When properly performed, it can reduce the length of overextended branches, decrease leverage, and reduce mechanical loading while maintaining the tree's natural form. Understanding leverage is one of the most important concepts in modern arboriculture because many tree failures involve the relationship between branch size, weight, attachment strength, and environmental forces. Not all trees fall in the same way. Every tree species has unique characteristics, including growth patterns, wood properties, branching habits, root systems, and response to stress. Some species naturally develop strong branch attachments, while others may be more prone to certain structural challenges depending on their growth form and environment. For example, many eucalyptus species are fast-growing trees that can develop long, heavy lateral branches with significant end weight. As these trees mature, proper structural pruning and regular inspection can be important for managing long-term structure, especially in urban environments where targets may be present. Many pine species can be susceptible to wind throw, particularly when growing in exposed locations or when soils become saturated and root anchorage is reduced. However, failure patterns vary between species, site conditions, and individual trees. A pine growing in a protected area with healthy roots may perform very differently from one growing in poor soil or an exposed landscape. Oaks are often recognized for their ability to compartmentalize decay effectively compared to many other species. However, even strong compartmentalizing species can develop defects, decay, and branch failures depending on their age, structure, environment, and history. This is why experienced arborists evaluate both the species and the individual tree. A species' reputation does not replace a proper assessment. When arborists inspect a tree, they are not searching for one single bad feature. They are building a complete picture of the tree's condition and surroundings. They evaluate the root flare and surrounding soil, signs of root damage or instability, trunk defects and indications of decay, major branch unions, cracks and cavities, dead or declining branches, canopy balance, previous pruning history, and environmental conditions affecting the tree. Arborists also consider the likelihood of failure and what would happen if a failure occurred. A defect in a tree located in an empty field has a very different level of concern compared to the same defect over a home, road, playground, or utility line. Tree risk assessment is about understanding the relationship between the tree, the defect, the environment, and the potential consequences of failure. Good tree assessment combines observation, biology, biomechanics, and professional judgment.